Hello and welcome to the Daily Space for today, Thursday, October 21st, 2020. I'm your host, Dr. Pamela Gay, and I am here to put science in your brain. Before we get started, I'd like to remind everyone that this October 24th and 25th, that's less than 2 days from now, this weekend, we're going to be holding a 36-hour-long hangout-a-thon right here on twitch.tv and the Now Media Network. This event is designed to help us raise the funding we need to keep this and all our other programming going through the 2021 fiscal year. Everything we do is funded through donations. Your bits, your subs, your patronage at patreon.com get us most of the way there for paying our bills, but we need a little bit more to make up the difference between mostly paying our bills and completely paying our bills. So please consider joining us. Learn more by visiting CosmoQuest.org. Okay, now getting back to the science. In case you hadn't noticed, this week the OSIRIS-REx spacecraft jubilantly dove down to the surface of the asteroid Bennu, reached into Nightingale Crater, touched the surface for more than 10 seconds with its tag arm, and then flew away up into outer space on a hyperbolic trajectory. Today, they're going to be maneuvering the spacecraft to get it back into orbit around this little tiny world. They're going to spin up the spacecraft to see if they can figure out just how much mass they picked up with, well, what I think is best described as an angry vacuum cleaner. And then they're going to figure out what they do next. So here's what happened. Starting on Monday, they began maneuvering the spacecraft into a new orbit so that instead of politely circling around this half-kilometer across world, they'd instead be getting closer and closer to the surface until eventually they dropped straight down. Originally, when they planned to do this, the plan was that they'd be using laser altimetry to figure out their distance away from the surface and just casually maneuver down, no big deal. Processing laser data is fast and easy. The problem was Bennu has a very, very busy surface. Instead of having the vast, fairly clear, smooth areas that we had anticipated based on images of the similarly sized Itokawa asteroid, what the OSIRIS-REx mission found was a surface with rocks and boulders on rocks and rocks on boulders. The CosmoQuest community, the folks that are part of producing this team, created citizen science software working with the team at the OSIRIS-REx mission at the University of Arizona that would allow more than 6,000 everyday people within the CosmoQuest community to map out all those rocks and boulders. And that data, in combination with all the other data acquired by the mission team, was used to figure out what are the safest places to possibly go down to the surface. Nightingale Crater was originally looked at and tossed aside as just way too dangerous. It turned out, though, that place with a giant boulder not too far away from where they touched and went, it was about the best they could get. This is a rocky surface of a rubble pile asteroid. The area that they touched down in was a few parking lot-sized parking spaces, was the size of a few parking spaces in a parking lot, and they were able to do it. They had to tuck up the wings of the spacecraft, the solar panels, to make sure that nothing was touched, and they got, hopefully, their sample. Like I said, we still need to figure that out. Now, here's the thing. When they extended the arm to touch the surface, They also fired off a nitrogen blast, a blast of gas. And this blast of gas was designed to throw up particles from the surface. This is part of why they were looking for a fairly smooth surface, someplace that hopefully only had fine particulate that would be easy to pull up into the instrument. The holes that they have are just 2 centimeters across. So while they can get a long rock, they could, for instance, suck up a hot dog if they wanted to. The other axes of whatever it is they're pulling up could be no bigger than 2 centimeters to fit through essentially their angry vacuum cleaner's nozzle. Now, they also had a variety of little sticky-ish pads that they could use to gather up material. And one of the things you might notice as the arm goes into the surface is there's a bunch of rocks there. And one of those rocks, it actually appears to have crushed. The hope is that the mission pulled up a little bit of this crushed rock, and we're going to have some freshly broken up samples. Well, not so fresh, but fresh-ish samples to analyze when the material gets back to Earth sometime in late 2023. Now, I've put a lot of caveats on the if they picked stuff up. There's the chance that just like sometimes your vacuum is unsuccessful at picking up that thing you see on the rug, well, there's a chance that this instrument was unsuccessful in pulling up material. If that's the case, they have 3 more nitrogen canisters that they can use to try 3 more times. They won't be going back to Nightingale Crater because they want to make sure they get a pristine sample that isn't contaminated by stuff of Earth that might be on the spacecraft. And because this complex surface required them to use computer vision to safely land. They took images of the surface ahead of time, programmed the spacecraft to look at where it meant to go, look at what its cameras were showing it, do the comparison to make sure that it was on track. And they guided themselves down by vision. Now, they disturbed the surface in the process, which means that their prior images wouldn't work for a second attempt. If they do need to go down again, the secondary spot that they picked that is most likely to be used is Osprey Crater. There is also the Kingfisher site and the Sandpiper site. So now we wait. We wait, and hopefully by Monday, we'll have some information on just what we can expect to hear. Next week, we will be having a member of the mission team joining us here on the Daily Space to tell us, well, what's latest from the mission. So we are all super excited, and when that sample gets back to Earth, it's going to be divided up. Part of it will go to Japan as part of a trade with the Hayabusa 2 team, where we'll be getting a sample here in the US from the asteroid Ryugu. These are 2 sibling asteroids, near-Earth objects that appear to be rubble piles. Additional parts of the sample are going to go to Canada to a team that helped building the OSIRIS-REx mission. Some of the sample we believe is going to be set aside, and then more of it is going to the University of Arizona for analysis. We can't wait. We just can't wait. But we have to wait. So let's move on to other science stories. Looking beyond one little rock and taking a fuller look at our galaxy, we have 2 new stories that look at the Milky Way's structure. Trying to figure out the shape of a galaxy we are inside is a bit challenging. Our view is impeded by gas and dust, and it is often hard to make 3-dimensional sense of our 2-dimensional images. These struggles get even more difficult when we're trying to make sense of the structures within gas clouds, those streams and shells of compressed gas that trace out the disk of our Milky Way galaxy. In a new paper appearing in Astronomy and Astrophysics with first author J.D. Soler, researchers let computers take their turn in understanding our galaxy. High-resolution, very large array images of the distribution of hydrogen gas were fed into a computer. And it was coded, that computer vision software was coded to look for the slight overdensities in the gas that mark areas that have experienced shocks or have been drawn together with gravity. The software was able to identify a 30,000 light year long filament of material, the longest material of its kind seen in our Milky Way galaxy. This hydrogen lane was named by the team Magdalena after the longest river in Colombia, the home of the lead author. According to researcher Jonas Seid, Magdalena could be the largest known coherent object in the Milky Way galaxy. We are lucky to have been able to spot it. In addition to this and many other expected structures laying parallel to the disk of the galaxy, the team also found bizarre structures pointing out of the galaxy. J.D. Soler explains, like in the spinning pizza dough, we expected that most of the filaments would be parallel to the plane and stretched by rotation. But what we found was vertical filaments around regions known for their high star formation activity. We knew we were onto something. Some process must have been blowing material off the galactic plane. Continued analysis of these structures is going to allow the history of our galaxy to be observed through the echoing shock waves of how dead stars and regions of star formation have compressed the gas. This research is just the start, and I can't wait to see what else they find thanks to a little help from computer vision. Now, in the images that we're showing you here, you can see at the top the unhampered regular image of our Milky Way galaxy in hydrogen gas. That bottom image, that is what the computer vision was able to identify. Sometimes computers can parse out things our own eyes are blind to. All right. The next story comes to us from a collaboration that includes one of the most prolific researchers in astronomy, Avi Loeb. Working in collaboration with Giacomo Faraghian, this pair looked at the motions of the stars orbiting closest to the supermassive black hole in the center of the Milky Way to see if they could use stellar motions to get the rotation rate of our black hole, Sag star. If you have a fast rotating black hole, one going up to as fast as the speed of light, it's twisting space-time. Well, and that twisting will affect the motions of objects around it, effectively scattering them more and more over time. This is like the effects of a hurricane on the motions of things trying to move near it. They simply get carried in new directions. If the black hole, however, isn't rotating quickly, there's no significant scattering effect. In looking at the S-stars orbiting the Milky Way's supermassive black hole, astronomers find two distinct populations orbiting in different planes. It's believed these are stars that formed from two distinct star-forming regions and have since migrated into essentially rings of stars, as the stars that formed a bit closer to the center of the galaxy have orbited faster over the eons, and those a little further away have orbited a bit slower. Since both these rings of stars are still well defined, Faraghian and Loeb calculate that our supermassive black hole, our Sag star, must be rotating no faster than 10% the speed of light. This speed has consequences to how our galaxy can behave. With this low speed, infalling material won't be whipped up into a quickly turning accretion disk that drives powerful magnetic fields that accelerate jets of material out of our galaxy. That's just not going to happen. In fact, our system is likely to remain jet-free through future interactions. According to Faraghian, this will also have an effect on future observations by the Event Horizon Telescope. Here, I'd like to admit this quote is how I learned there are planned additional observing runs of our galaxy with the Event Horizon Telescope. I can't wait to see what the processed images eventually show, and I look forward to seeing this result of a slowly rotating supermassive black hole confirmed by those future images. But until that happens, this has been the Daily Space.